So in this video, I will discuss about model courses of atomic structure. So in this session also I have selected some important models. We will discuss one by one. It is first question. Among the following groupings, which represents the collection of isoelectronic species? So what are isoelectronic species? Isoelectronic species are the atoms or ions having the same number of electrons. Very important topic. Isoelectronic. Iso means same. Electronic means electrons. Same number of electrons. Here atoms or ions carrying the same number of electrons are isoelectronic species. So here check C option. CO is given. CO. So for carbon, how many electrons will be there? 6 plus oxygen 8. Therefore 14 electrons in CO. Next, NO plus. NO plus means N. 7 electrons, nitrogen. Atomic number 7, 7 electrons. Oxygen 8 electrons. Plus means here removal of 1 electron. Therefore, minus 1. 14 electrons. Next, Cn minus. Carbon will be having 6 electrons. Plus nitrogen 7. Minus 1 means gaining of 1 electron. That means plus 1. Therefore, 14 electrons. Next, C2, 2 minus. Carbon 6 electrons, therefore 2 into 6 minus 2 means here take plus 2. 14 electrons. So here CO, NO plus, Cn minus and C2, 2 minus are carrying same number of electrons. Same number of electrons. Therefore, these are isoelectronic species. Therefore, correct option is C. Next question. The compound in which cation is isoelectronic with anion. Here also similar topic. Isoelectronic. That means containing same number of electrons. But here we have to compare cation and anion. First I am taking option A. Option A. What are the ions? Na plus. So how many electrons are there in Na plus? So Na means atomic number 11. Here plus 1 means remove 1 electron. Therefore 10 electrons. Next anion is Cl minus. Cl minus. Cl atomic number 17. Minus 1 means here take plus 1. 18 electrons. So these two are not isoelectronic. Different number of electrons. Check option B. In option B, cation is Cs plus, cesium plus. Cesium atomic number 55. Plus 1 means here take minus 1. Therefore 54 electrons. Next anion is F minus. F means atomic number 9. Minus 1 means take plus 1. 10 electrons. So these are also not isoelectronic. So Cs plus and F minus will be having different number of electrons. Check option C. Na plus 11 minus 1, 10 electrons. Next I minus. What is atomic number of iodine? Iodine 53. Minus 1 means here take plus 1. That is 54 electrons. These are all not isoelectronic species. Check option D. Cation is K plus. K plus means 19 plus 1 means take minus 1, therefore 18 electrons. Next, anion S2 minus, sulfide ion. Now sulfur 16 minus 2 means take plus 2, 18 electrons. Therefore, these two are isoelectronic. So in K2S, that means potassium sulfide, cation and anion will be having the same number of electrons. Therefore, option D. So this model is also very, very important. Here compare cation and anion. Calculate the number of electrons present in corresponding cations and anions. If same number of electrons are present in cation and anion, those two species will be isoelectronic. So for this calculation, you need atomic numbers of almost all the elements. Next question. The frequency of light emitted for the transition n equal to 4 to n equal to 2 of He plus is equal to the transition in hydrogen atom corresponding to which of the following transition? Here two cases. First case, for He plus, atomic number 2, that. Next, nu bar for He plus, which is equal to 1 by lambda of He plus, that is equal to, He plus is hydrogen-like species. For hydrogen-like species, Rydberg equation is nu bar He plus equal to 1 by lambda He plus, that is equal to RH into Z square into 1 by N1 square minus 1 by N2 square. This is Rydberg equation. Substitute these values. So for He plus, transition is already given. N1 equal to 2 and N2 equal to 4. That is given in problem. Substitute these values. RH into Z square, Z is 2 square 4 into 1 by N1 square, that is 2 square 1 by 4 square. So cancel with 4, we'll get nu bar for He plus equal to RH into 1 by 1 square minus 1 by 2 square. So this is expression 1. Next, case 2. For hydrogen, Z equal to 1 for hydrogen. We should find N1 and N2 values for hydrogen. Rydberg equation, mu bar for hydrogen equal to 1 by lambda H. That is equal to RH into 1 by N1 square minus 1 by N2 square. So this is expression 2. In problem, it is given that the frequency is same. Frequency means nothing but you can take it as wave number. Given 1 equal to 2. Equating two expressions, we will get nu bar He plus equal to nu bar hydrogen. That means 1 by N1 square minus 1 by N2 square is equal to 1 by 1 square minus 1 by 2 square. So therefore we'll get N1 equal to 1 and N2 equal to 2. So here it is transition from 2 to 1. In helium, 4 to 2 transition will be equal to 2 to 1 transition in hydrogen. Therefore, option A, very important problem. For He plus and hydrogen, frequency is same. Frequency means you can take it as wave number. Equating these two expressions will get N1 and N2 values. For helium, transition will be 4 to 2 and hydrogen 2 to 1 to get same frequency transition. Next question. In hydrogen atomic spectrum, a series limit is found at 1 to 186.3 centimeters inverse. Then it belongs to. The series we should find here. Series limit. So here in this question, in hydrogen spectrum, series limit is given 1 to 186.3 centimeters inverse. Then it belongs to. We should calculate the series. So in a Rydberg equation, u bar equal to 1 by lambda, that is equal to RH into 1 by N1 square minus 1 by N2 square. So here nu bar, series limit, that means wave number is given 1 to 186.3 centimeters inverse. And we know RH value, Rydberg constant for hydrogen atom, 109,677 centimeters inverse. And for limiting line, N2 will be equal to infinity. Therefore, Rydberg equation becomes nu bar equal to 1 by lambda, that is equal to RH by N1 square. So from this, N1 square equal to RH by nu bar. So RH value 109,677 divided by 1 to 186.3. So from this, N1 square equal to 9, that implies N1 equal to 3. So electronic transition from infinite level to third level. So since lower level is 3, this becomes Paschen series. So option will be C. Transition belongs to Paschen series. So nu bar is given, RH we know. For limiting line, that means series limit, N2 will be equal to infinity. From this we got lower level value. Electron transition from infinite level to third level means Paschen series. Next one. Two fast moving particles X and Y are associated with de Broglie's wavelengths 1 nanometer, 4 nanometer respectively. If mass of X is 9 times the mass of Y, then the ratio of kinetic energies of X and Y would be. Here two particles are given, X and Y. First, wavelengths. Here 1 nanometer and here 4 nanometers. Wavelengths are given. Next, if mass of Y is m, then mass of X becomes 9m. That is also given. Mass is also given. Mass of X is 9 times that of Y. Next we know de Broglie's relation. Lambda equal to H by root 2m into Ke. Here lambda x, mx and kex. Similarly, for lambda y, h by root 2my key. So this is expression 1 and this is expression 2. Take expression 1 by 2. We will get lambda x by lambda y equal to root over 2my key by 2mx kex. Substitute these values, we'll get. So lambda x 1 nanometer by 4 nanometer equal to root over 2 gets cancelled, my, that is m by 9m into ke y by kex. So m gets cancelled. Therefore, on squaring 1 by 16 is equal to 1 by 9 into key by kex. Here we should find, therefore, kex by key equal to 16 by 9. So kinetic energy ratio will be 16:9. Therefore option D. Just here comparing between X and Y particles. Wavelength is given and mass is also given. Mass relation is given. From this we are getting kinetic energies ratio 16 by 9 or 16:9. Next one. Ratio of magnetic moments of Fe3 plus and CO2 plus is. So we know magnetic moment formula, mu b equal to root of n into n plus 2 bm, which is unit of magnetic moment, Bohr magneton. Bm is Bohr magneton. So for Fe3 plus, configuration becomes d5. So d5 configuration, you know, half-filled configuration. 5 unpaired electrons, that is n equal to 5. Therefore, mu b for Fe3 plus root of 5 into 5 plus 2, root 35. Similarly, for CO2 plus, configuration will be D7. D7, you know. Two pairs and 3 unpaired. N equal to 3. So therefore, mu b equal to root of 3 into 3 plus 2, root 15. So here it is asking ratio. So this is mu b 1 and mu b 2. Therefore, mu b 1 is to mu b 2 mu b1 root 35 is to root 15. It is simply root 7 is to root 3. Option C. Magnetic moment calculation. So here n is number of unpaired electrons. Fe3 plus 5 unpaired electrons, CO2 plus 3 unpaired electrons. Next question. So Planck's constant value is given 6.63 into 10 power minus 34 joule into second. Velocity of light, we know that 3 into 10 power 8 meters per second. So which value is closest to wavelength in nanometers of quantum of light with frequency 8 into 10 power 15 second inverse? Simple question only. So we know lambda equal to C by mu. C value 3 into 10 power 8 meters per second. New frequency 8 into 10 power 15 second inverse. So we'll get this value as 0.375 into 10 power minus 7 meters. So 37.5 into 10 power minus 9 meters. So we know 10 power minus 9 is nano. That is n. Therefore, wavelength will be 37.5 nanometers. So approximately 40 nanometers. You can write 4 into 10 power 1 nanometer. This is the answer. So B is the answer. Direct question. 10 power minus 9 nano. Next question. Lithium and a proton are accelerated by same potential. Their de Broglie wavelengths lambda Li and lambda P have the ratio. So here mass relation is given. Mass of Li equal to 9 into mass of proton. So from this we can use de Broglie's relation, lambda equal to h by root 2m into qv. So your terms are lambda is wavelength, h Planck's constant, m is mass, q is charge, v is potential. Here potential v same. So therefore, so apply this relation for lithium. Lambda lithium equal to h by root over mass of lithium, the q of lithium, and potential v of lithium. Similarly for proton, h by root 2 mass of proton, charge of proton, and potential of proton. Here it is given potential is same for both Li and P. So from this, say this is expression 1 and expression 2. 1 by 2 gives wavelength of Li by wavelength of proton is equal to ratio 2 gets cancelled. Potential is also same. So the terms are root over mass of proton into charge of proton divided by mass of lithium by charge of lithium. Here you can take lithium as lithium plus. Take lithium as lithium 3 plus. Next here charge will be, therefore wavelength of Li3 plus by wavelength of proton will be equal to, substitute the values, you will get mass of proton. If mass of proton is 1, mass of lithium becomes 9. 1 by 9. Next QP, charge of proton. If charge of proton is 1, this becomes 3. So therefore, wavelength of Li3 plus by wavelength of proton equal to, so 1 by 27, that is 1 by 3 root 3. So D will be the option. Here consider lithium as Li3 plus cation. Relation between lithium and proton. Lithium 3 plus. Charge will be 3. Next question. Here uncertainty in position and momentum are equal, then uncertainty in velocity is. This is concept of Heisenberg uncertainty principle. Delta x into delta p equal to h by 4 pi. Delta x is uncertainty in position, delta p uncertainty in momentum. Here it is given delta x equal to delta p. So in place of delta x, I am taking delta p. Delta p into delta p equal to h by 4 pi. That is delta p square equal to h by 4 pi. So delta p, we know, momentum is mass into velocity, square equal to h by 4 pi. So from this, delta v square equal to h by 4 pi m square. From this, uncertainty in velocity equal to root over this value, h by 4 pi m square. That is delta v equal to 1 by 2m into root h by pi. Is uncertainty in velocity. 1 by 2m into root h by pi. So A will be the option. Heisenberg uncertainty principle. Next question. Ionization energy of He plus is 19.6 into 10 power minus 18 joules per atom. Then energy of first stationary state of Li2 plus is. Here ionization of hydrogen like species will be equal to, remember this relation, ionization of hydrogen into Z square is fundamental equation. So here two hydrogen like species are given. I am applying this relation to first Li2 plus, ionization of Li2 plus equal to ionization of hydrogen into Z square. Z is 3 for lithium. Therefore, it becomes 9. Say this is expression 1. Similarly, ionization of He plus Z equal to 2 here. So, ionization of hydrogen into 4. So, this is expression 2. So, expression 1 by 2 gives ionization of Li2 plus by ionization of He plus will be equal to 9 by 4. Next, ionization of He plus is given. So, therefore, ionization of Li2 plus is equal to 9 by 4 into ionization of He plus value 19.6 into 10 power minus 18 joules. So, we'll get this value as 44.1 into 10 power minus 18 joules. So, we know ionization of Li2 plus is equal to E infinity minus E1. E infinity minus E1. So, therefore, E infinity minus E1 equal to, I am making it 4.41 into 10 power minus 17 joules. E infinity value 0, we know. E infinity value 0, therefore, I am writing here. E1 value, which is energy of first stationary orbit, minus 4.41 into 10 power minus 17 joules. E1 is energy of first stationary state. So, option B. Yeah, joules per atom, inverse will not be there. Removing inverse. Joules per atom or simply joules. First expression is very important. Ionization of any hydrogen-like species will be equal to ionization of hydrogen into Z square. Z is atomic number. For any hydrogen-like species, ionization will be equal to E infinity minus E1. From this, we are calculating E1 value. Next question. Simple question only. Kinetic energy calculation. The kinetic energy of an electron in second Bohr orbit of hydrogen atom is. Here given second Bohr orbit, that is n equal to 2. Second orbit is given. So we know kinetic energy equal to half mv square. Next, from Bohr's postulate, we know angular momentum mv are equal to nh by 2 pi. So from this I am taking v value. V is nh by 2 pi mr. So substitute value of V in kinetic energy expression. Therefore, K equal to half into m V square n square h square by 4 pi square m square r square. So from this K equal to half into, so m and the m square gets cancelled. N square h square by 4 pi square m r square. That is k equal to 1 by 8 into n square h square by pi square m r square. Next here one more point. Radius of nth orbit we know. Radius of nth orbit equal to a naught. A naught is radius of first orbit of hydrogen atom. A naught into n square. So your second orbit is given, therefore R2, radius of second orbit equal to A naught into 2 square, which is 4. Substitute R2 in kinetic energy expression. Therefore kinetic energy equal to, we can write 1 by 8 into, in place of n, write 2 square into h square by pi square m, in place of r 4 A naught. 4 A naught square. Finally, kinetic energy will be equal to h square by 32 pi square m A naught square. This is final kinetic energy. H square by 32 pi square m A naught square. Important model. So from kinetic energy, first relation between kinetic energy and velocity. Next, velocity and radius. So here first expression, next velocity expression and radius expression. Three expressions are very, very important here. So here option C. Next question. Simple question, conceptual question. If nitrogen atom had electron configuration 1s7 instead of 1s2, 2s2, 2p3, which rule is violated? We know Aufbau principle, Pauli's principle and Hund's principle. It is obviously Pauli's exclusion principle. Why? Because according to Pauli's exclusion principle, an atomic orbital can accommodate maximum of 2 electrons with opposite spins. Here in 1s orbital, there are 7 electrons. That is impossible task. So clearly, Pauli's exclusion principle. Exclusion means here only. Any atomic orbital can accommodate maximum of 2 electrons with opposite spins. Here in 1s orbital, 7 electrons are placed. That is wrong according to Pauli's principle. So 1s7 configuration is violating Pauli's principle simply. According to Pauli, an orbital can accommodate maximum of 2 electrons with opposite spins. Accommodate. Maximum of 2 electrons with opposite spins. Maximum capacity of any atomic orbital is 2. But here 7 electrons are placed. Next question. In hydrogen atom, if energy of electron in ground state is 13.6, then the energy of second excited state is second excited state. So we know energy of electron in nth orbit minus 13.6 into Z square by n square electron volts per atom. This is general expression. Next, if it is taken as plus 13.6 into Z square by n square, so hydrogen atom is given for hydrogen atom Z equal to 1. Therefore, En becomes 13.6 into 1 square by n square electron volts. Here it is asking energy of second excited state. For second excited state, so second orbit is first excited state, third orbit is second excited state. Therefore, n equal to 3. Therefore, energy of third orbit equal to 13.6 by 3 square. So, which is given by 1.51 electron volts. So, A option. Energy of second excited state means energy of third orbit simply. Third orbit is second excited state. Next question. Limiting line in Balmer series will have frequency of. Limiting line of Balmer series. So in our Rydberg equation, mu bar equal to 1 by lambda equal to RH into 1 by n1 square minus 1 by n2 square. So for Balmer series, comma n1 equal to 2, and for limiting line n2 is infinity. So therefore expression becomes mu bar equal to 1 by lambda equal to RH by n1 square, 2 square, which is 4. So here RH value is given as 3.29 into 10 power 15 by 4. So which is given by 8.225 into 10 power 14 second inverse. This will be the answer. Option A. 8.225 into 10 power 14. Series limit of Balmer series. For hydrogen atom. Nothing is given means take hydrogen atom. Next question. The radius of first orbit of hydrogen atom is A naught. Then de Broglie's wavelength of an electron in third orbit is. It is given radius of first orbit of hydrogen atom A naught. Then de Broglie's wavelength of electron in third orbit. Is A naught. Next, radius of nth orbit equal to, we know, A naught into n square. Radius of nth orbit is A naught into n square. So here we must calculate de Broglie's wavelength of electron in third orbit. Therefore, given n equal to 3. Therefore, R3 equal to A naught into 3 square, which is 9. Radius of third orbit. Next, from de Broglie's relation we have n lambda equal to 2 pi r, standard condition. Here n is 3. 3 lambda equal to 2 pi into, in place of r, take r3, third orbit radius. Therefore, 3 lambda equal to 2 pi into r3, 9 A naught. Therefore, wavelength equal to 6 pi A naught. This is the wavelength of electron in third orbit of hydrogen atom. So, option C. Next question. In an atom, an electron is moving with a speed of 600 meters per second with an accuracy of 0.005%. Next, we should calculate the uncertainty in position. Uncertainty in position. So, given first velocity 600 meters per second and accuracy is given delta V, we can calculate in 600 0.005%. That means 0.005 by 100. It will be equal to 3 into 10 power minus 2 meters per second. Next, we know delta x equal to h by 4 pi m delta v. Substitute values here. 6.6 into 10 power minus 34 by 4 into 3.14 into, so mass is 9.1 into 10 power minus 31 into delta v 3 into 10 power minus 2. So therefore delta x equal to, so finally we will get 1.92 into 10 power minus 3 meters. Uncertainty in position 1.92 into 10 power minus 3 meters. So option C. This model is also very important. Next question. If kinetic energy of electron is increased by 4 times, then wavelength of de Broglie's wave associated with it would become. Simple question. De Broglie's equation, lambda equal to h by root 2m ke kinetic energy. So here m is constant. So I am taking ratio lambda 1 by lambda 2, initial and final values, root over ke2 by ke1. Here it is given kinetic energy increased by 4 times. That means ke2 equal to 4 into ke1. 4 into k given. So therefore lambda 1 by lambda 2 equal to root over 4, which is 2. So from this lambda 1 equal to 2 into lambda 2. Therefore lambda 2 final wavelength will be 1 by 2 that of lambda 1. So final wavelength will be half. That means becomes half. So option B. So 1 is initial, 2 is final. Lambda 2 is half of lambda 1. Relation between lambda and kinetic energy. Next simple question only. The correct set of 4 quantum numbers for valence electron of rubidium atom. So we know rubidium belongs to first A, that is alkali metals. So we know alkali metals: lithium, sodium, potassium, rubidium, cesium and francium. So corresponding configurations are helium core, neon core, argon, krypton, xenon and radon. So after completion of helium core, 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. Here rubidium is given. Valence electron of rubidium is 5s1. So for 5s1, the quantum numbers may be n equal to 5. Principal quantum number. Azimuthal quantum number 0. If L is 0, M becomes 0. Next, 1 electron is present. We can write plus half or minus half. Plus. So quantum numbers are 5, 0, 0, plus half. Option A. 5s1 is valence electron of rubidium. This one also simple question. Photoelectric equation. So we know energy of instant radiation equal to work function plus kinetic energy. Instant energy h nu, work function h nu naught plus half mv square. V is velocity of ejected electron, v square. So from this half mv square equal to h into nu minus nu naught. Nu is incident frequency, nu naught threshold frequency. So from this h into nu. Nu is again c by lambda and c by lambda naught of mv square. So therefore v square equal to hc into 1 by lambda minus 1 by lambda naught, that is lambda naught minus lambda by lambda into lambda naught. So from this V equal to root of 2hc by m to lambda naught minus lambda by lambda into lambda naught. This is the expression. 2hc by m into lambda naught minus lambda by lambda into lambda naught. Option C. So 2 times it was given in JEE Mains. Very important formula. So V is velocity, H Planck's constant, C velocity of light, M mass, lambda threshold wavelength, lambda is incident wavelength. Next one. This one also simple question. M and E are mass and charge of revolving electron in the orbit of radius r for hydrogen atom. The total energy of revolving electron will be. So we know total energy, or we can say En. Total energy En equal to sum of kinetic energy plus potential energy. Here kinetic energy is always positive and potential energy always negative. Next, total energy En equal to, what is kinetic energy? Kinetic energy means half mv square, potential energy negative kz e square by r. Since potential energy directly proportional to q1 q2 by r, where q1 q2 are charges of nucleus and electron respectively. R is distance between nucleus and electron. Again, En equal to half mv square is kz e square by r minus kz e square by r. Therefore, total energy equal to minus kz e square by 2r. So, in CGS system, K value, Coulomb's constant, will be equal to 1. And for hydrogen, Z equal to 1. Substitute these values, will get total energy En equal to minus E square by 2r. Minus E square by 2r. So, option D. Important topic. Calculation of kinetic energy, potential energy and total energy. So, here clearly you can say total energy also negative. Total energy always negative. Potential always negative. Kinetic energy always positive. Ionization enthalpy of hydrogen atom is 1.312 into 10 power 6 joules per mole. What is the energy required to excite electron in an atom from n equal to 1 to n equal to 2? Excitation energy we must calculate. So n equal to 1 lower energy level, n equal to 2 higher energy level. That means here we can say delta E equal to final minus initial, E2 minus E1. Here ionization energy is given, therefore energy of nth orbit becomes minus 1.312 into 10 power 6 by n square joules. So from this E1 value is minus 1.312 into 10 power 6 by 1 square joules, and E2 is minus 1.312 into 10 power 6 by 2 square joules. So from this delta E equal to 1.312 into 10 power 6 common, 1 minus 1 by 4. So 1.312 into 10 power 6 into 3 by 4. So which is equal to 984 kilojoules. 984 is the answer. So option A. So this much amount of energy is required to excite electron from n equal to 1 to n equal to 2. Next one. Similar question. Here energy of electron is given in joules per atom. In previous question it is given in joules per mole. Here joules per atom. What is the wavelength? Here in this question they are asking about wavelength. Wavelength required to excite electron from n equal to 1 to n equal to 2. Planck's constant velocity are given. So energy of nth orbit minus 2.178 into 10 power minus 18 by n square. For hydrogen atom Z equal to 1 joules. So E1 minus 2.178 into 10 power minus 18 by 1 square joules. And E2 is minus 2.178 into 10 power minus 18 by 2 square joules. So from this delta E equal to E2 minus E1, so which is 2.178 into 10 power minus 18 into 3 by 4. So this value is 1.6335 into 10 power minus 18 joules. So from this we can calculate this is delta E value. We know delta E is Hc by lambda is 1.6335 into 10 power minus 18. Therefore lambda value equal to, so we know Hc value 19.875 into 10 power minus 26 H into C value by 1.6335 into 10 power minus 18. So from this lambda value will be equal to 1216 angstrom units. 1216. Here in options it should be 1216. Option D. One two one six. Option D. Important question. Energy to wavelength calculation. In previous question direct energy calculation, and here energy to wavelength conversion. Next. The dissociation energy of H2 is given 430.53. If hydrogen is dissociated by illumination with radiation of wavelength 253.7 nanometers, then calculate percentage fraction of radiant energy which will be converted to kinetic energy. So this is nothing but photoelectric effect. So first given lambda equal to 253.7 into 10 power minus 9 meters. Next, energy of here mole is given per mole. Calculate for mole. N0 into Hc by lambda. Energy for 1 mole. 1 mole of hydrogen atoms. N0 is Avogadro's number. So N0 6.022 into 10 power 23 into Hc value 19.875 into 10 power minus 26 by lambda value 253.7 into 10 power minus 9. So from this we'll get incident energy as 472.2 kilojoules. Next, dissociation energy is given. Dissociation energy 430.53 kilojoules. So therefore kinetic energy equal to incident energy minus dissociation energy. So which is 472.2 minus 430.53. So which is equal to, so here percentage we should calculate. Percentage of kinetic energy equal to 472.2 minus 430.53 divided by initial value 472.2. Therefore, percentage of kinetic energy equal to 8.76%. So option B. Option B. Next question. What is the de Broglie's wavelength of electron in ground state of hydrogen atom? In ground state of hydrogen atom. Here we must find wavelength, de Broglie's wavelength of given hydrogen atom in ground state. Ground state means n equal to 1. Given ground state n equal to 1. Ground state. Kinetic energy is given 13.6. 1 electron volt is also given. So use de Broglie's relation H by root 2m into kinetic energy. So lambda equal to H value 6.625 into 10 power minus 34 divided by root 2 into, here mass of electron 9.1 into 10 power minus 31 into kinetic energy 13.6 into 1.602 into 10 power minus 19 joules conversion. So from this we get lambda value as 0.3329 into 10 power minus 9 meters. So which is 0.3329 nanometers. This will be the answer, 0.3329. So option C. This is also important model. So energy required to break 1 mole of Cl-Cl bonds is 242 kilojoules per mole. What is the longest wavelength of light capable of breaking single Cl-Cl bond? Velocity and Avogadro's number values are given. So here energy is given 242 kilojoules 10 cube joules per mole. Therefore, energy equal to 242 into 10 cube 6.023 into 10 power 23 joules per molecule for one molecule energy. Next, energy equal to Hc by lambda, which is equal to 242 into 10 cube by 6.023 into 10 power 23. So from this lambda value will get 0.4947 into 10 power minus 6 meters. So by converting it into nanometers, 494.7 nanometers. This is the wavelength. 494.7 nanometers. Your options are not given. Take it as numerical based questions. 494.7 nanometers. Simple calculation only. Just we have to convert kilojoules per mole into kilojoules per molecule or joules per molecule. Next question. So deuterium nucleus contains deuterium. Deuterium is D12 or H12. D12 or H12. So Z equal to 1. That is equal to 1 proton. Next here 1 is atomic number and 2 is mass number A. So A minus Z gives number of neutrons. A minus Z. 2 minus 1, that is 1. So 1 neutron. So deuterium contains 1 proton and 1 neutron. So option will be A. 1 is atomic number, 2 is mass number. A minus Z gives neutrons. Next question. The total number of atomic orbitals in 4th energy level of an atom is. 4th energy level means 4th orbit, n equal to 4. So number of orbitals in an orbit will be equal to n square. So therefore, number of orbitals in 4th orbit equal to 4 square 16. 16 orbitals. Direct question. So option C. Next question. The energies E1, E2 are given. Take ratio between E1 and E2. 25 is to 50, which is equal to 1 is to 2. Wavelengths. Energy and wavelengths are inversely proportional to each other. Then it becomes 2 is to 1. Therefore, from this we can write lambda 1 is 2 times of lambda 2. Lambda 1 is 2 times of lambda 2. So relation C. Simple question. E equal to Hc by lambda. Energy and wavelength are inversely proportional to each other. Next question. Here it is given different subshells. Here it should be NP. Here it should be NP. So N equal to 6 is given. N equal to 6. Sixth orbit. So here orbitals will be 6s. I am calculating here N plus L value. That means energy. 6 plus 0, 6. Next 5d. N minus 1 d is there. N minus 1 d means 5 plus 2. 7. Next 4f. 4 plus 3. 7. N plus L value. 6p. 6 plus 1, 7. So according to Aufbau principle, electron first enters into the subshell which is having lower N plus L value. So first 6s. First 6s will be filled. Next, these three are having same N plus L value. Same N plus L value means same energy. Then compare N value. If N increases, energy increases. The electron enters into the subshell which is having lower N value. Then second place will be 4f. Third place 5d. Fourth place 6p. Then here order will be 6s. After completion of 6s, 4f. After completion of 4f, 5d. At last 6p. This is the sequence of filling. See, it is present in option B. 6s, 4f, 5d and 6p. Order of filling which is based on Aufbau principle. Next question. So according to Bohr's theory, which are the following transition in hydrogen atom will give rise to the least energetic photon? Least energy means difference of delta E. Calculate difference of delta E. That means delta E. We will write a diagram. As the N value increases, difference between energy levels decreases. Like this. One, 2, 3, 4, 5, 6. So energy increases in this order. Energy axis. So as the energy increases or as the N value increases, difference of energy decreases. See here 6 to 1 maximum amount of energy, 5 to 4 medium amount of energy, 5 to 3 medium amount of energy, 6 to 5. Here it will be minimum energy gap. So therefore, if electron jumps from 6 to 5, it will give photon of least energy due to least energy gap between 6 and 5. Therefore, option will be C. Calculate here difference of energy between two energy levels. Delta is minimum for 6 to 5 transition. It will give photon of least possible energy. So option will be C. So these are some important model questions which I have selected. That is the end of these questions.